So thus far in the class, we've been focusing on just linkages. Now we're going to look at an alternative type of mechanism in the next couple of lectures here, which are cams. And cams are used in a variety of places, but ultimately they are function generators that are taking the input and coordinating it with the output. So in this introduction lecture, we're really going to talk about what cams are, what kind of role they play, what types of machines you see them in, and then getting into some of the fundamentals of the motion programs that you might use for them. So first of all, what is a cam and follower? So a cam, this is really just a specially shaped piece of material, typically metal, that's used to move the follower in a controlled fashion. And the follower is really the link that we're interested in as our output link, and this is what's constrained to either rotate or translate. So what you see in the figure right here, this happens to be a rotating follower that is spring-loaded into the cam. So a cam follower, and very often we can have followers that are moving in a linear path, lots of varieties of followers. So another way of looking at a cam is taking what we've learned from mechanisms in linkages and saying, let's apply that to a cam, and really thinking about it as a form of four-bar or a degenerate four-bar, where if I take the center of curvature here of each one of these links, so I've got my cam, and I can think about this as being my input link, I've got my coupler link that's going between the two centers of curvature, and then back down to my output link here. That really is a four-bar that instantaneously approximates or creates the motion that the cam mechanism would be following here. Now you can imagine that as I move the cam, the center of curvature is changing, and therefore the approximate four-bar is changing. But we can approximate it as a four-bar, and everything that we've learned about four-bars thus far of transmission angles would apply here, which we call pressure angles for cam mechanisms, or things like doing velocity analysis. You can simplify it into the four-bar to do those. So where do we use cams? One of the very classic applications is in internal combustion engines to open and close the valves that allow fresh air fresh air with fuel into the engine, and then close those valves to allow the combustion to happen, and then open the exhaust valve to allow the spent gases out of the engine. Very common application. Also control of machinery in a variety of industrial applications where you might have a linkage or just the cam itself, but the cam then provides the timing for the mechanism and really does the function generation, and often is used then for timing that event relative to other events. So let's say that you're picking up a part from a nest, placing it somewhere else, maybe you need to do a spot weld operation on it. Well, your cams are what are providing the timing as well as the amount of lift or motion that you need to create. Often they can be used for force generation, whether or not it's a can crusher or a rock crusher, but you can do a lot of force amplification, just like you can do with a linkage type of a force multiplier. And they can also be used for very precise positioning. In some applications, they will precisely position an end effector within either 1/1000th of an inch or a 5/10,000th of an inch. So you can have very precise positioning with cams. So let's look at a couple of these applications. Here's the internal combustion application, where on the left side you'll see more of the traditional overhead valve, where near the kind of closer to the side of the engine you will have a camshaft that is rotating around. It is acting on a hydraulic lifter right here, so that's the follower. It's pushing this push rod right here, and then this is acting as a bell crank, pivoting right here. We call it the rocker arm. And then it's forcing this valve to move downwards and open and allow gas either in or out of the engine. More modern engines typically don't use all of that connecting linkage and go to an overhead camshaft, where this camshaft right here is driven by the crankshaft, typically through a timing belt or a timing chain or maybe gears. And then this, as it rotates, will act on these roller followers, which then cause these bell cranks to rotate and ultimately push the valves for the intake or for the exhaust. So a very common application in engines, and as we change the profile of the cam, we change what the timing is of those valves. An industrial application might look something like this. This might be a pick-and-place mechanism or something else where we're assembling pieces of some industrial device, and we will have multiple cams typically driven on a common camshaft or maybe multiple camshafts, and they are timing multiple events. So we might pick up one piece, place it here, bring in another piece, place it next to it, and then having a separate attaching event, whether or not it's an epoxy or a weld or something like that. Now, an application that is surrounding what you're looking at right here is a hydraulic pump. So in the picture you see a 3-lobe cam, which is the same thing that I have here. And in that picture you'll see 5 different pistons that are being actuated. So this is a hydraulic pump, a piston style pump, so ultimately I have a piston moving back and forth inside of a cylinder. I can look at the linkage here, and each one of these is a 4-bar linkage that's then being actuated by the cam mechanism. So I've got a 4-bar being actuated by the cam, making it a complete 6-bar mechanism if I look at the effective linkage that could approximate this. And so the really interesting thing here is that as I rotate this, you'll see that I have a camshaft that's rotating around, and every full rotation of this gives me 3 different lifts, or 3 different reciprocations of my piston in the cylinder. So I get 3 pumping strokes per revolution of my pump. What else we can do with this camshaft is we can carefully design in what the profiles are, such that when I'm adding up all 5 cylinders of this pump, I actually get a very smooth flow rate out of the pump. So by carefully controlling what does the cam profile look like, I can make sure that the addition of the flow rate coming out of the pump is almost a constant, even though I've got 5 different cylinders that are actuating in a sequential order. So those are the types of things that we can do with cams that would be very difficult to do otherwise with a linkage. All right, so we've seen some cams here. This happens to be a radial or a plate style cam, but let's look at some other ones. We can have a variety of radial cams. Like I was saying, we can have something like this guy right here, which happens to have, we can have one that looks like this. It happens to have a track in it, so it moves the follower radially, but it happens to be following in a track. We can have some stationary axial track cam, something like this, another plate style cam, another radial or plate style cam, another one with a pretty aggressive profile to it. This would be a barrel cam where the shaft is rotating in this direction, but the follower is moving in the axial direction. So we can have a variety of cams. Some of them happen to be only segments that we're using. So all of these happen to fall into the areas of cams. Just like we have different types of cams, we can have different types of cam followers. 2 of the more common ones are a roller follower, such as what you see on this mechanism here, where I have a roller contacting the cam. Or I can have a flat face follower, where I have a flat piece that is connected to the translating element, and then that's being driven by the cam directly. Often in the roller followers, we will either have plain bearings, but more often needle bearings or other types of rolling element bearings, which maintain low friction, but we still lubricate these joints because we can often have very high stresses between these contacting elements. All right, so we've got different cam types, we have different follower types, and I have a number of other follower types that I'm not talking about here. We can also close the cam joint in different ways, and this means keeping the follower in contact with the cam. A very common way to do this, such as done in this pump right here, is with a force closure, where we're using a spring or a weight or something else to force these 2 together and keep them together. And when we're designing this, we have to pay attention to the dynamics such that when we get up to high speed, we don't get cam float where the follower leaves the cam and then comes back and slaps into it, causing additional wear. And if you run an engine at very high RPMs, this will sometimes happen and you can hear the cam lobes floating on the camshaft. Now, an alternative way, if you don't want to have a force closure, is to go what's called a form closure, where we capture the roller follower in this case in some sort of a groove or a track, and this then allows us to basically drive it in both directions or pull it back as well as push it out. And we don't have to have a spring closing it. Now the challenge here is that you have a roller which is now in a groove, and you have to allow a little bit of slop between the 2 of them so that it's not contacting both of them at the same time, because you can imagine it's only going to roll on one side at a time. When it's touching the other side, the roller is going to roll in the opposite direction. So anytime that's reversing, it will create a little bit of impact as it's moving from one side to the other, and it will start rotating in the opposite direction, causing some friction between the 2. So there are trade-offs with both the form and the force closure. Another way of creating this closure is called a conjugate cam, where basically your follower is moving on 2 different cams at the same time, which are conjugates of each other. So in this case, we have an oscillating follower, a rocking follower, which is touching 2 different cam conjugates, cam conjugate 1 and 2. And these are precisely machined such that as it rotates, it is basically staying form closure to these 2 cams and is oscillating back and forth, but we're now not moving from one side of that groove to another as we were with the form closed. We can do similar things with barrel cams where we can have a tracked groove or a rib type of a barrel cam. So these are both form closure. We can also force close these with springs. And where you often see barrel cams is in a rotary indexer, where you can imagine I've got some sort of a table that I want to rotate and then pause and then rotate and then pause. When it's pausing, I'm often doing some operation on an assembly, and then I want to move to the next part, and this index is between them. Well, very often we have barrel cams that are in there that are rotating. So you'll see right here, this happens to be my barrel cam that's rotating against these followers. And I have multiple followers here. So in this case, I have 6 different positions that I can dwell my rotary table as I'm moving through the range of motion. All right, so when we're designing cams, we usually take whatever cam profile it is and then start to lay it out on a 2D space so that we can visualize it a little bit better. And then we start to talk about the cam motion programs. And what we mean by that is really, what does this look like as far as dwells where we're pausing, and do we have dwells or not, and what are the 2 endpoints can look like. So in some cases we will have a rise fall where we simply move up and back down and we don't dwell at either end. We can have a single dwell with then a rise and a fall to that dwell. Very often we have a double dwell where we might pick up a device or a part at one location, move it up to another and dwell at both of those. Or we can have multiple dwells where we're rising and falling in between them. And we're going to find that we have to develop different motion programs for each one of these specific tasks. And usually we break it up into segments where we say, all right, we know the dwell segment is very easy to generate, but what does the rise segment look like? Or what does the fall segment look like? And we can develop the programs to achieve the motion we want. So this is what one of these cam timing diagrams might look like, where I have a low dwell and a high dwell, and you'll notice here that the x-axis happens to be the angle of the camshaft, either in theta, or we can convert that into time if we know the angular velocity of the camshaft. And here I'm going from 0 to 360, so at this point we would be then moving back to 0 degrees again and moving through our cycle. And what we're going to focus on quite a bit in the coming lectures is, what do these rise and fall sections look like? Do I draw them as straight lines? Do I draw them as some other profile? And how do I determine what that profile should be? That's where we're going to focus. And what we're going to find is that we're not only going to look at position, but we're going to start to look at the derivatives of the position to get the velocity, the acceleration, and one more derivative of the acceleration to get the jerk. And so very often we'll talk about SVAJ diagrams. Position, velocity, acceleration, and jerk. And we'll be designing at all these different levels such that we get a smooth cam profile that minimizes the acceleration forces, minimizes the kinetic energy, and minimizes the vibration. So that's where we're headed with this.